This is one in a series of several videos on how to use the SolarGen Interactive Configuration Tool. This first one will be sizing with a string inverter, no optimizers. So the first thing we do every time we design with this tool is to select a module. So we go to the top and select from the database, and there are thousands of modules in the database. Probably the one you're looking for is here, and just select it and the data will fill in automatically. And if you for some reason have a module that is not in the database and you'd like to enter it into the database, you can select the 0 position and then put your data in here. So just put it in off the module data sheet, and when you get to the temperature coefficients, make sure you put these in as negative numbers and percentage per degree C. So just put in, minus 0.28, 0.35, whatever it is. The length and width, this is in inches. So once you've selected, and we have picked the Hanwha QCell 300 watt module for this example, and we have no optimizer, so we're going to skip beyond that. We'll drop down and then select an inverter. At this point, you can do one or two things. You can either select an inverter, which is what we've done here, and see how big of a PV array you can actually put into this inverter based on a ratio. And we're using 1.25 to 1 as a ratio from PV array to the inverter. You can go up to 1.35, or some inverter manufacturers allow up to 150%, 1.5 to 1. That's kind of extreme for a residential inverter, in my opinion. 1.25 is a good safe area to work with. We also make an adjustment for elevation. So it's elevation divided by 33,000 gives you a reduction in capacity, or oversized capacity, based on the higher radiance that you'll experience in a higher elevation. So we have this example set at 4,000 feet, so it takes that 125% ratio down to 113%. So now we have a 1.13 to 1 ratio as opposed to a 1.25 to 1 ratio. So it tells us we can put in a PV array of 5.64 kW into this 5 kW inverter. Now there's another way to look at this. If you want to just go up and deselect this, let's go up and take that out and put in the PV array size. We have a drop down that says square footage or PV array kW. And let's say you already know that you want to put in a 5.4 kW based on the wattage of your modules and the size of the roof. It automatically tells you that you need an inverter rated at least 4.78 kW. Well, the increments are usually in 1,000 watt, increments. So we would go up to a 5 kW. So we'll leave that in. Go ahead and select this. You'll notice that we have microinverters selected first, and then beyond that is the string inverters for residential, and then beyond that is string inverters for commercial. Let's go back up into the residential, and we're looking at an SMA transformerless 5 kW, 240 volt. So we're looking at the AC voltage to identify this inverter, match it up. So 18 is our selected number of modules based on the PV array size we wish to have. And we know if we were to take that out, it would tell us 18.8. So either way, we're looking at 18 modules so that we don't oversize this PV array to the inverter. So we have temperature parameters in order to adjust for the number for the coldest day voltage that we're going to experience. So we have to go to the ASHRAE tables or to the local weather service and find out what the minimum mean temperature is and the maximum mean temperature, and put it in these two cells right here. So we've selected minus 10 and 35 for our two extremes. Once you've made that selection, you want to also put in your normal operating temperature increase during the middle of the day. So when we're in direct sunlight, which increases the temperature on the cell, then we have a factor. It's usually about 25 degrees, so I just leave it defaulted there. You can change it to whatever you want, whatever you think the real life increased temperature is. So you may be on a very high irradiance area, and you may be mounting these very close to the roof. And if that's the case, then you may want to kick that up to 30. And it's going to change your numbers slightly down here. So let's go back to my 25 standard. And we see that the calculations are made for us, and it determines in order to not go over 600 volts max, we can only put 13 modules in series. And in order to not go lower than 175 volts minimum, then we can have as few as 7 in series. So we have all these selections available to us. Now you'll notice on the inverter data sheets, they often show these days an operating range and then a max efficiency range. So we try to stay within the max efficiency range, and that's what this is defaulted to, not the actual operating range. This may go down to 100 volts minimum, but the efficiency is drops a little bit from what they warrant. So we have 18 modules. We have 2 independent MPP inputs in this inverter. Some of them have 3, but in this one we have 2. So we don't have to have the same number of modules in series in each one of these inputs. In this example, we're doing 9, and we're doing 2 parallel strings of 9. So this falls within our range of options. We could have 10 here, and then have 8 if we wanted to. We still have 18 modules. So it's up to you. Whatever you decide, you'll need to select which of these columns you picked, or if you picked a combination of both, and select either 1, 2, or 1 and 2. I selected 1 right here, so that's the information that's pulled down and being fed off to these other tabs. So before we go to the other tabs, and we're going to look at the line diagrams and size our conductors, let's look at the bottom of this page. As we scroll down, you'll notice there's another secondary inverter. This is primarily for commercial systems. Sometimes we use 2 different types of inverters within the same PV system, and in that case, you have that option. Residential, you're probably not going to do that. So let's drop down below all that. We have a box here that's for inner row shading for ground-mounted and rooftop or commercial systems, so we're going to ignore that right now as well. What we do have is the next little box is just the orientation of the modules. We're placing these on the roof railing running east-west, and so the modules are in portrait formation. You can change that to landscape if you are running north-south. I just have it at portrait. So each one of these rows, you want to set exactly what it is. I've seen PV arrays where they do so many in portrait, and then they'll have one at the bottom because they don't have enough height left, but they have enough in order to turn the module in a landscape formation. So sometimes you see that. You do have that option to range it. And it'll give you the total width in inches or feet, and then the total height of the PV array. So there's no drawing tool where you can see it actually laid out. This is giving you the dimensions that you can lay out on your drawings. All right, let's go to the line diagram tabs. We have 5 different line diagram tabs that we can select from. The first 2 are commercial 3-phase. The next 3 are residential. We have load side, line side, and then microinverter. The load side is most common connection that we have with residential systems. However, there are some tariff programs that require you to connect onto the line side. If so, the only difference between these 2 tabs is one shows a line diagram connected to the line side, and the other one shows a line diagram connected to the load side. The information you input is exactly the same. So let's go to the load side. We see that our module data was fed over, and our inverter data is fed over. We see the line diagram, and it's numbered for the different parts and components as we go through. We drop on down a little further, and we see the number in series. If we had 2 different ones in series, like 10 and 8, and that would be represented here. We just have 1, and we have 2 strings identical. So it tells us what the fuse of each string should be, what the coldest day temperature is, and the operating voltage. So we have the max voltage on the coldest day. This goes on to our DC label, and this is what we calculate voltage drop with. So we need both of these. Then we drop on down, and it has an option here to select between parallel or combined. Now, most PV systems on residential, if they're roof mounted, all of your conductors are going to be run parallel down in the conduit all the way down to the inverter. If it's a ground mounted system, you do have the option of putting a combiner out there. And if that's the case, then it would increase the current because you're combining these two strings into one string, so the ampacity increases. So you'd have to size your conductor from that point to the inverter based on the combined outputs. So let's go back to parallel because that's what we're doing. And we just have we have 4 conductors. We have 2 parallel strings running down. And so we're sizing our conductors for each of the circuits. So we have our max current provided for us here, max current provided for us here, and then the ampacity requirement of the conductor and overcurrent device if we needed one. And then we have to find a conductor that's rated for 15.3 amps. So you hover right here and it says, hey, you need to look at table 31015B16. So, okay, where do I find that? You can go to the NEC, open it up, look for it, or you can use the embedded tables that we have. So you double click on this, it'll open it up, and select down. The smallest conductor that we can use with PV systems is a number 14, even though it would appear that the number 16 has the ampacity we need. We can not use that. So 14 is a minimum, so we'll use that, and it has a 25 amp rating in the 90-degree column. So most of our equipment, our DC equipment these days is rated 90 degrees, and our conductors certainly are. So this would typically be the column that you used to find the ampacity of that conductor. So we have a number 14 rated at 25 amps. Click out of that. Put that data in. 25 amps is the rating. And now we have a derate factor. Well, this is because the 31015B16, this table, is based on 30 degrees C. If your temperature in your environment in which the conductors are running is higher than that, then you have to derate them. And also, if you run more than 3 conductors in a conduit, you have to derate them for that as well. So we have 2 derate factors. So we're going to open this up. There's another table specifically for PV systems. It's in 69031, but it's an identical table as far as these 3 columns are concerned when you get beyond this temperature. All they do is disallow us to increase the rating for cooler temperatures with these. So we would look at the temperature, and what do we select? We selected 35 degrees as the minimum max temperature. And we go into the 90-degree column, and it's 0.96. So that's 1 derate factor. We have how many conductors? We have 4. So we're going to go into the derate for more than 3 conductors. It says if you have 4 to 6 conductors, you have to derate to 80% of the value. So we take 96% and 80%, and that drops us down to 0.77%. So we put that in, and that reduces that 25 amps to 19 amps. But this only has to be greater than the continuous current that we calculated up here, and it's 12.2, so it's a long ways above it, so we're in good shape. Next thing is voltage drop. We would go to table 8, click on this, open it up. Increase that a little bit. So we look at stranded cable, number 14, that says 7 strands, it's stranded cable. 3.14 is the ohms per 1,000 feet. So we use that and put it there. And then we want to put the one-way conductor length. This calculation is based on the 2-way conductor length. So don't put that in ahead of time. Just put in the one-way conductor length, and it'll multiply times 2 for you. So it shows we have 1.4% voltage drop. Well, that's acceptable as long as the AC side voltage drop is not excessive. Next thing we're going to look at is the equipment grounding conductor. We do have 2 circuits running in this conduit, so we have to have a grounding conductor that is equivalent to the ampacity of both those circuits. So the max current times 125% of two circuits is 30.5. And we go to the 251.22 table. And for a 30 amp overcurrent device or a 40, the number 10 is the minimum size. So we'll use the number 10 grounding conductor. You can go larger on the grounding conductor if you want. If you think that there's potential for lightning and you want to give it a better pathway, you can increase it. There's nothing saying you can't, but you can't go smaller than a number 10. So the next thing to do is size the conduit. So it depends on what kind of conduit you're using as to what size you'd use. Number 14, we have 5 conductors. Actually, we have 4 number 14s and 1 number 10. So we want to think about that. And let's go open this conduit size table. Let's open, increase the font a little bit. We drop down. What we're looking at is electrical metallic tubing. Let's just assume that this is what we're using. More than likely, if you're running through the attic, we're probably going to use flexible metal conduit. But if you're running on the surface of the building and down to the side of the house, more than likely you're using EMT. So let's assume that we are using this. Drop down until we see the wire type. If you're running in conduit on a building, you're probably using THHN. So we just keep on dropping down. And here it comes. So we have number 14. It shows we put 12 conductors in a conduit. If we were running all number 10s, we'd put 5. So we actually have 5 conductors, and 4 of them are number 14. So we could use a 1/2 inch. It'd probably be easier if you ran a 3/4, which is the second column here. So we have 1/2 inch, 3/4, 1 inch, and therefore. So 1/2 inch is what we picked. We do the same thing on the AC side. So this is the PV input, and this is the AC output from the inverter. So we have the continuous current rating of the inverter here, and then the circuit rating has to be 125% greater than that. So here's our ampacity rating. And here again, we go to 310/15V16, and it shows that a 30 amp circuit requirement is a number 10 conductor. So we can go back down here and open this up and go through that, but I'm not going to put you through that pain once again. And then our equipment grounding conductor, just as it was on the DC side, is a number 10 based on this overcurrent device rating. And then we go into, technically, you're supposed to go into table 9 of chapter 9 instead of table 8. This is for AC. It looks a little bit different from the DC table 8, but the numbers follow pretty close along. So it shows for number 10, 1.2 ohms per 1,000 feet. And for the DC side, it would show 1.24. So there's not a lot of difference in it, but you're supposed to use this table instead of table 8. Okay, so we put that in, 1.2, and then we look at the conductor length from the inverter output to the AC connection point, load center. 20 feet is what we have in this example. So our voltage drop is 0.5%. Total voltage drop is 1.9. So just under 2%, that's acceptable. Here's our overcurrent device, number of conductors, and as we saw before when we looked in the conduit using EMT, we could put up to 5 conductors. So we have 3 conductors, line 1, line 2, neutral, and ground. So that's 4. So that's 1 under the max for a 1/2 inch. It's probably a pretty straight pull, not a lot of bends, so 1/2 inch would probably be easy enough. If you have a few bends, a few turns, then you may want to go to the next size up 3/4. It's always easier to pull, less likely to damage conductors as well. All right, so that's the line diagram. We've sized our conduit and our conductors. We just have to do a little label work now. So we have these locations, 1, 2, 3, 4, 5, 6, and we have some labeling. Let's take a look. On the DC side, the DC disconnect label, which is probably right on the inverter, we have the max voltage and max current. And then for all the source circuits coming in to the inverter, on the building and in the building, we have to put this warning sticker on. And then we have to list this is the DC disconnect. So if this has both this and that on that, this is redundant. And then, of course, if we have rapid shutdown on the DC side instead of the AC side, then we'd have to have this over on the DC rapid shutdown device. We're not showing one in this example, but if you're on the 2014 or 18 code, you would have to have it. And these two labels are probably not necessary, but there's always a possibility. Then we go to the AC label, and we have the AC disconnect, and we have max current and the operating voltage. And then more than likely, this is going to be the location of the rapid shutdown system. We have to have labels at the interconnection point and a warning sign at the load center where we tie that breaker in from the inverter. It's probably going to be an overcapacity of the main load center. So in that case, we have to place this warning, do not relocate device. All right, so that wraps up all the design portions of the system. Then we can click over onto the SolarGen tab. And what we're looking at here is a little bit of production analysis. So our location is Atlanta. We have the solar radiation defaulted here. You would need to go to PV watts or use Pathfinder reports, whatever you're going to use. Find out what the radiation is for the location and put that in for each month of the year. This is a derate factor. We have 2% in there defaulted as voltage drop, and as you saw, we had 1.9, so that's pretty much it. The inverter efficiency is pulled over. PTC rating comes from the California Energy Center database, and for this module, it shows 92.9, so we're losing 7.5%. So the net efficiency, brand new startup, is 87.9. If we were to look at the maybe 3 months in, we may have a loss factor of 3%, something like that. So you can take those out if you want. And then we're going to look at performance over time and maybe do a little levelized cost of energy. So we look at analysis period 25 years, degradation of the PV array output 0.5% per year, and then availability. Is the grid up all the time? Are we producing every day? And then the net cost after incentives, put those dollar amounts in there, and that'll give you your levelized cost of energy. So this is not a financial tool, but it does give you a little bit of extra information. Well, that wraps this up, this video, and the next video we're going to do is with interactive systems, string inverters with optimizers. Thanks.